Hi, in a previous mailbag video I showed this Haasoscope oscilloscope schematic and how it was an example of probably one of the worst formatted schematics I've ever seen, and I mentioned that this could be a good example to show how to lay out a schematic properly. You know, some good design techniques, industry conventions, you know, rules of thumb to follow, and just some good habits when laying out a schematic. So a lot of people actually said, yeah, I'd love to see that. So here we go. And I think in this particular case, it's probably better to start out with a badly formatted schematic, not only to show you what the good schematic layout techniques are and good practices are, but to show you what's bad and what doesn't work and why. I think that's just as important as showing you the good techniques. So I think this is a really good baseline that we're going to use here to just tidy this up. So I'm going to show you how to turn this higgledy-piggledy dog's breakfast mess into this nice schematic here. Stick around. Could take a while though. Now here's the original PDF schematic, which I'll link to the GitHub down below for the Haasoscope, and I think we'll start out by just going through some of the, you can already see, some of the bad things that are going on here. So I thought we'd do a video tidying this up, completely tidying this up from scratch. Now, unfortunately, this was done in Eagle. I don't know how to use Eagle, and I don't really want to learn how to use the Eagle schematic editor just to do this video. So what I've done is I've actually imported this into Altium Designer, and you can see that it's practically identical. It's got all the same issues. There's a few differences, like for example, take these like nets, you know, a few font rotational things and stuff like that. If we compare that with this over here, you can see it's like, you know, it's actually a bit tidier already in Altium Designer than it is. Look at these, like they're backwards, and those labels there for the JTAG, they're all backwards and over this, and it's just like it's terrible, Muriel. So anyway, but it's pretty darn close to the original PDF. The Altium import, Eagle import, actually did very well. So we're basically starting off with the same framework. It's just going to be easier for me to use Altium, which I'm familiar with, to do this. So let's go. Let's first look at some of the bad things that you shouldn't do in schematic layout. And by the way, I'm recording this in 2K, so if you want to watch it in its native resolutions, that's just this screen that I'm using. It's a bit harder to capture in 1080p. It's just a smaller working window. So first of all, what I'm actually going to do is I've got the original version of the schematic and I've got the new tidy version, which I haven't done anything to yet, and we can actually show differences. We can actually compare the differences between these two schematics. So we can do that, and we should tell us that there's no differences. So at the end of this, the idea is to keep all the nets the same, because the first rule of schematic layout is that everything must be electrically connected properly. For example, let's just go in here. Now, of course, a good schematic tool, you've got to set your snap grid. And of course, a good schematic tool will actually snap to the hotspot of the pin. You can probably see that big X on there for that pin. It's, you know, I think it's changed all the defaults in Altium. I'm not going to muck around, but it will actually snap. And if that's not electrically connected, if you don't set the snap grid properly, you can be like 0.1 millimeters off that or something like that, and it's not going to make electrical connection, and then that is not going to generate a correct net list, which then goes into your, which then exports into your PCB or imports into your PCB, so that you can then do design rule checking. And using an electronic CAD package like this for schematic and PCB design, it's all about electrical rules checking. So that's the first thing you're going to want to do when laying out your schematics, set your snap grids. Now, unfortunately, this one is all, because it's imported, it's all off the grid. It's not something that we would have done from scratch. It'd be much tidier. You can actually, you should be able to see the net in there as we actually do this. And like, it's just a lot of it's not going to line up like it would on a normal grid designed from scratch. So just be aware of that. But snap grids are the number one thing, and electrical connections and snapping to the correct pins and connections to generate your netlist is the most important thing in laying out a schematic. That's before we get to the visual part of it. Now we're going to talk about the first convention in schematic layout, and this particular design, in this case a 4-channel oscilloscope, is a decent example of this, because we're going to have analog signals coming in and then we're going to have like digital signals coming out. It's an ADC basically. So the first convention in schematic layout, now you don't have to do this, but it's kind of expected in the industry, and if you don't do it, it shows that you're not a professional design engineer and you don't know what you're doing. Signals always flow, or should flow by convention, from left over to right. I've got to do it back to front on the camera here. Left to right. So it's got to start on the left-hand side here, and so signals, if you've got signals flowing into whatever project it is, they should be on the left-hand side, and then they should be processed, go through amplifiers, do whatever, and then slowly work their way over to the right hand side here. Now, because this isn't a 4-channel oscilloscope, where's our B and C's? If I looked at this, if I came to a schematic, oh, this is the schematic for an oscilloscope, great. I'm looking for the B and C's. Where should they be? They should be over here on the left hand side, but they're not. We've got the power supply over here, we've got an oscillator, we've got a JTAG header, we've got some other things. Where are the B and C's? Well, they're actually hard to find. They're buried away in here. Here they are. So there's just so many things wrong with this. Not only are they incorrectly placed on the schematic for correct signal flow across your schematic, but they're also rotated incorrectly. Look, I got to go like that to look at the look at the B and C's. It's absolutely ridiculous. And look, the grounds are upside down for starters. That's the next thing. Your ground should always be going down. Now, the next rule of schematic design, look at the lines on here. This instantly, when you immediately see the schematic, you just go, like, what's going on? These lines are like, these ones are okay. They're going down like this. That's fine. Lines should never be, as a general rule, never be on an angle in a schematic. They're up and down, left, right. That's it. Okay? So it's by having the lines come down like this is just like, you would think, like, why? Why would anyone do that? It's absolutely ridiculous. And not only that, but look at the nets here. The nets are just like, you can't tell which one's what. It's absolutely ridiculous. And no, this is not an import issue. This is in the original schematic. And not only the original PDF schematic, it's in the original Eagle file as well. So I don't know what, look at this. Going down like that. Like, there's just no reason for that to be a thing. Now, the next thing is never, ever have lines going through your chip symbols like this. Look, we've got the FPGA and there's lines going through it. Never, ever do this. That is just insanity. And I've got the same thing down here. Look at this. Look, this is our chip, right? This is an op-amp. You can't even tell it's an op-amp to start with, and well, that might be okay. Some people like to use the op-amp symbol. Some people prefer to use the chip, the actual physical chip symbol, and that's fine. There's no real convention there. It's up to the individual designer to do that, but never, ever have your lines going through your chip like that. It just makes absolutely no sense whatsoever. Now, in the case of, as I just said, the chip layout versus the functional op-amp symbol, the op-amp symbol is going to be easier to understand, because you would have to go up and go look up the MAX 4416 to know that it's an op-amp to start with. You can probably get an idea from the net labels and the pin labels and stuff like that what it is, but it's better to do it as an op-amp symbol. But if you want to do it as a chip, that's okay, but it's not as easy to read. And in this case, look, all the text is like, the text is upside down. Like, the annotation for the symbols. This is not an importing issue. This is the original schematic. Goes without saying, they should be the right way up. Now, here's a small thing, but once again, you've got the ground up the top. That makes absolutely no sense. If you're going to have these LEDs laid out in this configuration, this horizontal configuration like this, flip it over so that the ground is on the bottom. Now, that being said, having vertical, like these LEDs like this in a horizontal configuration doesn't make sense. So what I would do is actually rotate all these so that they're vertical, so that you don't have to tilt your head like that to read the annotations. And of course, it goes without saying, why is this zigzag in here like this? But, you know, we'll tidy that up. But it just makes more sense to put that in a vertical configuration so that you can just read all the text without having to go like that. Unless there's some physical reason, because a lot of people like to match their schematic physically with their PCB. So if the LEDs are on the PCB in a horizontal configuration, people might want to, you know, a designer might want to keep it on the schematic as a horizontal configuration, and that's okay. That's why also some people prefer to have their chip pinouts like this. They prefer to have their pinouts in the physical order of the chip. So 1, 2, 3, 4, 5, 6, 7, 8, so that when you're troubleshooting your board, it's easier to map the pins on the schematic to the physical chip. And as I said, that has pros and cons both ways. It's better for troubleshooting to lay it out like that, but understanding the schematic, it's better to have the actual circuit symbol in there, in this case the op-amp symbol like that. And you know, there may be a similar sort of things for the LEDs, but I would definitely put that vertically. Just rotate selection like this, boom. See, that's just going to be much easier than we drag our no, it's yeah, because this is an import and nothing's aligned to the grid. It's all pretty horrible. Anyway, we want to move our ground. You'd move that down to the bottom there, and it's going to be much more readable. We need to flip around the orientation of the designators here like this, but as you can see, that's just much nicer. Now, speaking of which, how do you do the designators? In this case, you have a designator like this, and you have a value for, in this case, a resistor like this. Some people prefer to put them either side like that, and it depends on how you've got them laid out. Others prefer to have it like all up on one side, for example. Once again, there is no convention as long as it's consistent. You don't want to mix it up higgledy-piggledy in your schematic. So if you're going to do it, you know, it's probably okay to do it like that. We need to change our snap grid there so that we can get in there. But that's, you know, in this case, it's probably okay to do it like that, I'd say, because there's enough space between the components. But if you want to all put them on one side on the top or on one side on the bottom, just be consistent over your schematic, that's all. But sometimes you just are forced to mix and match because your schematic in one part might be like denser layout, for example. You just want to fit it all in, whereas it might be more sparsely laid out in another part. And in this particular case, we've got, for an oscilloscope like this, this is a relatively simple schematic, okay? I would want everything on the one page, and start the flame war now against those who prefer everything to be on one page if possible, or whether or not Altium were a big proponent of having things on separate pages, because this is all about modular design, for example. So you might have just the processor on one page. You might have just the power supplies on another sheet, or another sheet is the industry term instead of page, and another sheet there. Then you might have all your IOs on another sheet. Yeah, let's not get into the flame war. For an oscilloscope like this, I love to have everything on one sheet. But sometimes it doesn't print out on like an A4 sheet. It's too small, you can't read it. And hey, granted, I don't like that either. But, you know, so pros and cons both ways. I'm not going to get into that argument. So here we go. I'm just going to go in there and override the snap grid a little bit and tidy it up. See? So that's nice and neat. You keep your designators nice there, you know, and you want to go in there and fuss and get them all, you know, right. And you want to, this is where your snap grid comes in. You know, if this one's like over here like this and this one's sort of over here like this, it's just not going to look great when it's all lined up. You want everything lined up and perfect. Symmetry is a good thing in schematic layout, trust me. So, but once again, this is not the best example because we haven't laid it out on the proper snap grid from the start. I can like change all these parts so that they move them all to the snap grid, but then that can screw up the net list, and I don't want to do that. So It's not the perfect example. And once again, look, unfortunately, these are not evenly spaced out. See the differences? This has a larger gap between it here, 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 all that sort of stuff. If we were laying out from scratch, they'd all be consistently spaced and everything would be perfect. So I can actually go in here and align to grid like this, and it will put everything on the grid. Now it's going to snap, because when I actually rotated all that stuff, like nothing lined up. So in this particular case, we're good to go, and now we can actually draw our line. Oh, no, at the end of that, look at that. The electrical hotspot there isn't going to meet. Oh, look at that. Look at that. Once again, this wouldn't happen if you had proper drawn schematics from the get-go in the package. So a few of these quirks are specific because we've imported the thing here. So sorry about that. And that's the other thing to do with snack grids. When you're actually creating components, you don't want to set the center of your component to the graphical center. Always set your pins when you're laying out a new component to the snap grid. And now here's the eternal argument. Do you show the footprints in this particular case? Here we go. It's the footprint for this particular lead. Generally, you do not show that information on your schematic. It's just clutter. So you want to go in there and you want to hide that particular item. And yeah, in some cases, it can be valuable to have that on your schematic, but for the case of a lead like this and resistors and other stuff, no, it makes absolutely no sense to have that sort of stuff visible. Now, the next thing we want to do is in terms of nets. Now, when you've got like, you know, data buses coming off like this, you generally don't want to have data buses running right across your schematic. Some cases, and sometimes it's good, like if you've got, say, this chip here with these lines here and they're connected over this chip, you might just draw them straight across like that. If you've got your two chips side by side, that's okay. But in this particular case, if you've got here it is, D0A, right, all this sort of stuff going over to your FPGA over here, you generally don't want to be running snaking all of your traces across. Now, a good program like Altium Designer will have like buses, for example, and you can have them go into buses, and people like drawing then a big thick bus, which then goes over, so you just draw one big thick bus line, so it goes in, and that can look very nice and very professional, but you don't necessarily have to do that. In this particular case, it's nice because you could show that this particular bus, like, you have to hunt around. When D0A, well, where does that go? You've got to look around your chip. D0A, I don't know, is it down here? Is it over here? Like, where is it, right? Whereas if you had it as, if you drew that as a bus, you could physically draw the bus going up there and around. Now, I'm not going to go to the effort to draw the buses here, but by all means, do that. It's very nice, very professional. It shows where the signals go to without having to run like 8 or 16 lines all the way around your schematic. Now, the next thing is how you line them up. This is actually done perfectly. It's already done for us. You have a little bit of line going out here, and then you have the net name on top. You always put them on top by convention, and they're all nicely lined up. Look at that. That's beautiful. Why couldn't they have done that over here? What's going on here, and what are these ones here just flapping around in the breeze? I don't understand. Don't have stuff flapping around in the breeze. This thing should be all the way over here. They should be there. Didn't like me doing that, did it? These should be all the way over here like this, and then that should be there like that, and they should be all consistent on your chips, just like on this side here. So we'll just tidy all those up there like that. Got a few little issues down here. Once again, it's because we didn't lay this out from scratch. It's really rather annoying. And like, what's this? Upside down. Give me a break. Come on. Seriously? Like, and what? You don't use a net like that for 3v3. Like, you've mixed ports, electrical ports like this with nets like that. Don't do that. Have it actually going up to the actual port like this. So you would have that connected over to there like that. Didn't automatically junction up. Beware of that. So in this particular case, this is like really messy. Let's put it like that. Then let's have our ground connection over here. Okay, we can kill that ground connection like that. And I don't, you know, you could do this several ways, but basically we're connecting that up. That's not great because we're off the grid. And then you could have this connected over to here like this. No problem. Let's put in 2 junctions. The other thing is, why have we got these bypass caps just flapping around in the breeze over here? What are they associated with? Right? Put it next, if you're going to have the bypass chip, like have the bypass cap on the actual pin like this. And in this particular case, by the way, you've got this, like, it's just untidy to have this line running down to ground like that. If you're going to do that, edit your part, because this part does not have the proper physical pin order. So you would go in there and modify your pin so that this pin, this clock minus pin, I know it's nice to keep them together like this, but you would keep them together. So you'd move clock positive and clock negative down to here, this empty space down here, and then, because this is just going off to a net, clock positive, then you could have clock negative going down to the ground, and you don't have to have this wire going all the way up there. Just avoid crossing wires if at all possible. Now, in this particular case, let's have a look where this net that's just flapping around in the breeze, let's have a look at where that's going. Nowhere. What? Dora the Explorer clock is going nowhere. I don't understand what's going on there. And that's another thing, like, if you're not, there's no point labeling nets if they're not going to go anywhere. So we should just kill those, and there's just, like, there's simply no point having those. Maybe if you want to give them, like, the name's already in there, so actually calling them the same thing over here, and then have it, if they're not electrically going anywhere, don't label them at all. Just physically don't connect them. And again, this is crazy. You got the ground point. Not only is the ground symbol upside down, but it's actually on the upper side. And, like, follow some consistency here. So if you're going to have this cap, like, put it next to this cap here. Have this coming out like this. Like, it's not rocket science. And then you can join those 2 traces like that and have the one ground symbol like that. It's much nicer. And in this case here, these are nets going off, presumably they go off somewhere else. Let's, no, I was going to say these nets go off somewhere else, but they don't. But if they did, you wouldn't put the net just on there like this. What you would do is move it out like this, right? And then have them coming out, because it signifies that the signal is coming out like that, okay? So that's just nicer. Oh, it's not the best because we're off the grid, but you get the idea, okay? You have them going off like that, so it signifies that the signals are either coming in or going out, and yeah, you just don't have them like lying in the middle of the net like that. Actually have an extender line coming out and put the nets on the end of the line. And personally, I find this part a bit messy. Here's all the VCC pins, okay? You've grouped your different decoupling capacitors together. That's nice. You want to do that. If the 3 decoupling capacitors, in this case, you know, it's not uncommon to have a 10 mic, a 1 mic, and a 0.1 mic, for example, to get the different impedances. I've done a whole video on why you should why you'd put multiple bypass capacitors in parallel near a chip. Anyway, it's a bit messy having this line running off here. I would simply have the VC, like I'd have this physically near it. So I'd actually get rid of that line there, and I'd just add a extra net down here like this, right? Just put the extra net on there like that, and then just have all this like physically close to the chip like that. It's just nicer. Minimize the lines running across your sheet. Or in this particular case, I would, you could argue that, well, you could, move this down, move this up, and put the capacitors and physically extend the line across here, and then just run the capacitors down like that. But either way works. You just wanted to get rid of that little line, little daggy line in there. And likewise down here, just optimize space. This is just like too far away from these pins over here. Just move it closer. Do yourself a favor. There you go. That looks nicer. And we can, tidy that up. Once again, we don't need that Invisible. And once again, when you've got two capacitors like this, whether or not you put the ground and V, some people like to put it in the middle like that and then split off to the two capacitors. Others like to have it off to one side, like this, for example. They prefer to have it like that and like that. For example, I know that's a bit messy. Once again, it's the grid. Either way, it doesn't matter. Just put it physically close and neat and tidy. Once again, power on the top, ground on the bottom, near the pins that you're actually decoupling. And just a small thing here, don't have this line like this. You know, like keep some consistency. Well, keep some consistency like that. It's not gonna snap. But you know what I mean. And of course, this connector here, we're going to have to do something about this. Not only is it all upside down, but it's kind of, you've got the lines running through the connector. There's everything wrong with this. So let's flippity-doo-dah that around like that. And well, now we're starting to be a bit better. Now, here's one thing. This ground symbol, what do you do with this? Let's say you had to put the connector like this, and your ground pin happens to be the one at the top. It's really annoying. Traditionally, ground should be at the bottom. So, you know, there's a lot of people who will say, well, it should be like this, and then you should, you know, draw your trace going around like that. And that's okay. Nothing wrong with that. That's perfectly acceptable. Or you could keep it sideways like that. Maybe you could put it up here like this, and then you could, in this case, the ground symbol's quite large. So you could have it going up like this. Either way, you know, it doesn't really matter. Even some people, and even I've done this before, I've actually put them vertically, like horizontally, like that. So I actually spin it around like that to fit between pins and stuff like that. I've had a visually small ground pin. You generally want to avoid that. So, you know, something like that would be okay, or the other one down here, as I said. Either way, once again, this is a bit messy because the ground, everything's out of proportion because this is not properly designed, laid out from scratch. It's an imported project, but you kind of get the idea. I kind of would have actually preferred it down the bottom there like that. So I think that's better. Now, what do we do with this trace here going through our chip? Would you like, well, let's say that you need this connector here. Look, most of the lines for this connector are going to these up here. So would you actually run them all down here like this and over there? You might if you're physically constrained because this chip has to be here for some reason. But generally, you'd probably want that connector right up near the pins that you're actually going to be doing over here. So that'd just be a nicer way to do it. But once again, I can understand wanting to have the connectors physically away from your schematic. So you might have all your connectors on one side over here and just use nets, for example. 6 of one, half dozen of the other, as long as it's neat. You generally want to avoid all these wires running right across your schematic like that. So in this case, virtually all your signals except for this relay down here, or switch, is it? And yeah, it's a physical switch. And this one line going right over to the other side are all the connectors. So I'd be of the opinion to maybe shove that connector just in there. Either that or nets, shove the connector over to the side somewhere, as long as you're consistent. So in this case, we can go over here like this, and we'll move it up there. We've got to change our nets around and stuff like that. But yeah, we could tidy that up. We can sneak that in there. I think it's probably going to be better. And these net names, you wouldn't have them over here like this. You'd bring them over here to match. So this is actually going to be much nicer if we do it like this. Here we go. Look at that. How much neater does that look already compared to before? I know these are a bit higgledy-piggledy in here, right? But that is much nicer. So this net here, okay, is buggering right off to the other side of the chip over here. You wouldn't take that line all the way around. So you kill that trace there, and you would have the net, and then copy that net all the way over here, like so. There you go. And just get rid of all this crap running right across like this. There you go. That's nicer. And the other thing here, see how we've got this line going over here? It's like crossing here, here, and here. It's crossing 3 lines. It doesn't need to. So, of course, you would, select the right wire. You drag that like that. That's much nicer. And generally, you'd actually have it probably like that. And this one here, you drag that out of the way. And once again, just have them crossing as fewer lines as possible. This one's and once again, this one is crossing here. Doesn't need to. So that one will come across there like that. And that's just much tidier already. So no worries. And of course, the problem we've got with this net here is that you wouldn't have that come across all those lines like that. So you'd actually just draw that in. You know, you might draw something like that, for example. And that's just nicer. And there we go. That looks much neater. Once again, you could argue that that's better, that, you know, if you want to put all your connectors right off to one side, but that's certainly better than the original one that we actually had here, which was going down like that all over the shot. Even if this was nice and tidy down the bottom, I think it's just much nicer to have that connector in there like that. And just a small thing, tidiness, once again, right, you would actually rotate that so it's like that, and you don't want these lines coming across the pins like that. That's just silly. So you bring it out like that, and that's much nicer. And the same deal up the top here. Bring that around, and once again, you wouldn't have that horizontal like that. Whoop. Make it vertical. Much nicer. And there's far too much space in here, and the nets should be over the line. So we want to go in there and move those across. Much neater, much more compact. Everybody happy. And again, we've got this line where the nets are over. Even if the nets were here like this, okay, you might think, okay, those nets are relatively neat. But once again, it's really, you should be implying that this line is going out like this, okay? Because this isn't like an I squared C line, so you want to put them out like that. So it just visually signifies that there's a line coming in. That's much neater. And as for vertical resistors like this, do you put them off to the one side like that? Generally, I would, if I've physically got the room. I'd only put the annotations and the values vertically like that if I didn't actually have space. Sometimes when you've got all like a big group of resistors bunched together, you know, you might have to like put this either side like that. I've often actually done that, and when I've got them all grouped together like that, sometimes, you know, visually you don't have the space, but in this particular case, we have the space, and putting them both like that is just much nicer. You don't have to tilt your head to read it. So put everything horizontal, or designate as horizontal, if you've got the room to do it. And these connectors up here, take a look at this. There's no reason to have any of that vertical. So I'd get that, and I would rotate that like that. Then you get your ground, you fix that up, you get your 5 volts here, you maybe fix that up like this, you have it going up like that. Of course, we have to rotate all our nets here, but, you know, like, that's going to be much neater. No doubt. We don't need the component designator. So pin display, like, you could keep that in there like that, and once again, you wouldn't have some reading in that direction, some reading in the other. Generally, you're going to want them all reading, just like the spine on a book, reading from that direction. And this JTAG header here, look at the white space just wasted and resistors not lined up and stuff like that. No. Maybe you want to line them up all like that. There we go. That's nicer. Get them physically lined up across like that. Take up much less space. Thank you very much. I'll tidy that up. And another thing, just keep consistency on your designators here. You see that we've got, if you're going to have your designator on the top and your value underneath, make sure you are consistent with that across your entire schematic. Otherwise, it's just going to look a bit unprofessional. Now, if you remember this connector that we tidied up over here, that's called pin right. There's another one over here called pin left, and that's going off, a couple of traces going off Oh yeah, over to this side as well. So you would tend to group those physically together. So I'm tempted to move those, like we kind of sort of might have to shift the rest of this over, but I'd probably put this one over here next to it. Or because one's physically right, one's physically left, I don't know, you might argue that it's better on this side. You would have to actually go in and see where all these nets, these nets go over to here. So, yeah, it's higgledy-piggledy to all the pins. Once again, if you're laying out a schematic and you have a choice of the pins, in this particular case, okay, all of our pins are in physical, well, they're not quite in physical, they are in physical order around the chip, like this, pretty close to it. And once again, for a large chip like this, you might, a lot of people will do that, and there's nothing wrong with that at all. It can be a good thing, as I said, when you're troubleshooting and stuff like that. But then it makes a difference when you're trying to group your stuff together in your schematic. So if you either decide to go for the full physical pin configuration around your chip, or you decide, nope, I'm going to group my functions together, and then you would have, in fact, then once you do that, and your pins, you can swap your pins willy-nilly inside the chip. Once you decide to do that, you wouldn't have any of these crossover lines in here like this. You just have all the pins going straight in and then rearrange the pins on your chip. So it's all just neat and tidy like that. But then you don't get the physical pin configuration. Yeah, everything's a trade-off. And just a small touch here, because these are like the same type of connector. One's called pin left, one's called pin right. Just make sure that if you put pin 8 at the top on one and pin 1 on the bottom, be consistent with the other one over here. Now, you've heard me mention consistency before in schematics, and it's very important, not only like a placement of things, you keep all the text in one orientation, for example, like reading, like tilting your head like this and reading the same direction, keeping them above and below, and all sorts of stuff. It also extends to the schematic symbols themselves. In this case, we have the two traditional types of schematic symbols. We have like the dual plate one like that, and we also have the one with the flat top and the curved bottom, and there's no consistency. They've mixed and matched both there for both low value items like non-polarized capacitors. Then if we go over here, we've got different types of resistors. We've got the square one here, bit of a square resistor fanboy, but I've got, a bit of nostalgia for the old zigzag resistor one. Doesn't matter which one you use, makes a rat's ass difference, but be consistent in the types of schematic symbols that you actually use. It's important. Right, so now we really have to reformat this thing, because this was my first thing with this schematic that I went, this is so bad. Not only is that B and C connector rotated like that, there's no left-right flow in it, and then look, having we've got 4 200 ohm resistors in parallel here going down to ground. Not as only a ground symbol upside down. This is actually a switch symbol here. It's not very good because it doesn't have like the circular contact, so the switch symbol's not drawn properly, stuff like that. But that's neither here nor there. So we need to like reorient this whole thing, and it's not going to be fun. So the first thing I'm going to do is just split these things up, because really we want to be able to rotate this and then put it in the right orientation. I won't bore you with all the details of tidying this up. That's not the point. Okay, so what we've got here is this abomination where the resistors are on this side here. It didn't make sense vertically, and it doesn't make sense horizontally either. The B and C is the input for this entire project, so you want it to be on the left-hand side of your schematic. Remember, input signals on the left, flow through your page, output signals on the right. So first of all, we want to get this poor B and C. Well, let's just get it out of here, right? So we want it to be like over here like this. All right, now we don't need 2 ground symbols, so we'll get rid of that and we'll just join 1, right? So this is now starting to make a lot more sense. So how do we orient the switch? I don't know. You could like maybe have it like that, perhaps. Yeah. That switch is better off being horizontal like that. Actually, this is going to be much neater if we just do it like that. Okay, so we've got our input signal like that going through our switch, and then it's obvious we don't want to, remember, no diagonal lines on here, and then it's obvious that, bingo, that's much nicer. And then, of course, the input has to bypass this like that, and that will go off to the rest of our circuit. Now, that's much more obvious, and then we can do something nice, like here's where we start adding some niceties to our schematic. Then we could maybe add a note there like that, 10 meg 50 ohm termination like that. So, you know, it just makes it obvious that what that part of the circuit is doing. If it wasn't electrically obvious, just adding like little notes and things like that can make a huge difference. And of course, you'd probably like do this at the end. You wouldn't necessarily like, well, because this is duplicated, you'd add it now so that when you duplicate this in your schematic, it'd just copy over. But often you'll do like a note annotation thing at the end where you finish your schematic electrically and it's all okay, and then you'd go through and just, you know, add like nice little notes and little formulas and other little niceties around your schematic. So this one here requires a bit of thought. Okay, we've already got our photo MOS relay like this. It's a MOSFET in there with a diode which then switches it off. It's basically an electrical, a MOS relay. It's just like a regular contact relay. And because the switch contacts are here and here, I guess you could argue that, well, okay, you know, we should probably like have that in line like that. But the problem is, so that like your input signal, here you go. So your input signal goes in here and then it comes out here. But then that's not a use of, that's not a good use of like compact space, especially if you look at how much vertical height is required there. It's actually more than the original schematic like this. So, you know, you might just bring it down like this or something. And then of course we've got our ground upside down. And so we have to look at rotating this one around. It's not particularly great. I'm not a fan of this. That's sort of, you know, fairly descriptive. Okay, your signal comes in here. That B and C connectors, I know, it's back to front. It's drawn back to front. I'm not going to bother editing the symbol. It's just, it's like the signal comes out physically out of the B and C, or out of the B and C that way. It's just, it's nuts. Anyway. That's a very poorly drawn symbol to begin with. But let's not go there. Anyway, and then that, of course, bypasses around here, and it's obvious that input termination is nice. And then this is obviously your photo MOS relay for your AC coupling. So it selects AC coupling or DC coupling. And then we've got a 10 meg resistor going to ground on this side here. And, well, we haven't finished drawing our input signal like that. There we go. And then we've got our LED driver up here to turn the relay off and on. And a big part of schematic design is choosing good net names, descriptive net names. I mean, there's no limit to how long you can make your net name, usually, apart from, you know, like physical limit, like looks really long. So you don't want to put war and peace in there, right? But in this case, E, I don't know what E stands for. Enable, that's probably enable. Like ACSW, it's obvious to me that that's AC switch 4. Just AC switch. There's no need to put the E and underscore on the front of it. It's just obvious. Like AC switch 4 would have been fine. But, you know, descriptive net name, choosing descriptive net names, a bit of an art in itself. Actually, I've decided what I'm going to do is I'm actually going to flip this up, because it makes no sense having this signal come down to the bottom and the LED up there. So rather than redraw the symbol, I'm just going to work with what we've got, and I'm actually going to flip it around, flippity-doo-dah, like that. So that's going to be much nicer, so that our signal flow is straight in like that, our AC coupling like that, and once again we'll get rid of this, because that's untidy, and then we'll take our resistor and we'll move that around and we'll rotate that, get rid of that, bingo. I know this looks messy because we're not on the grid, okay, but, you know, stick with me. And here's another thing, okay, don't put 0.01 microfarads. I know there's lots of decimal point fanboys out there, but decimal points can get lost when you do printouts and stuff like that. That's why you would call that one either a 10 nanofarad. Okay, this is actually, there was a time back probably mid-80s, early to mid-80s, I think it was the great nanofarad debate, where, like before this, they never actually used nanofarads in schematics. It was microfarads, and you put 0.001 microfarads, or you'd put picofarads. There, nobody was using nanofarads back then. Anyway, but it's all changed these days. So you'd put that as engineering notation, right? Proper engineering notation without the decimal point. 100 nanofarads like that. Or some people prefer to 0U1 like that. They actually put the multiplier in the middle of where the decimal point would normally go, for example. So, you know, look, that's 10n. So that would be 0n01 like that. But you would, like, no, I'd prefer 100 nanofarads, thank you very much. Or just 100n, something like that. But don't try and avoid decimal points like that. So there you go. Already it's looking like a much nicer schematic. It comes in like this. We've got our switchable input termination, and then it flows in. We've got our AC coupling off or on with the control down the bottom of that. We've got a 10 meg resistor on the output, and then we just take the rest of this and just line that up like that. Once again, maybe you got some dead space down there, so to do that you might sort of, you know, have it down here like this, and then have your wire go up there like that. Either way, you know, it's okay. Now in this particular case, because they're so, like, they're close, physically close together like this might be somewhere where I'd actually put the designator on one side and the value on the other side like that. I know we're sort of mixing them up here. Here's top and bottom like that. This is top and bottom. You know, we could put it like that, but then it might be too close to the one down below. So whether or not it's side to side like that or one above the other, it doesn't really matter. It's, once again, consistency is key, okay? So if we're going to put it like that for that one, then we'd keep it like that for that one, and so forth. Now, whether or not you actually put one top bottom, here we go. It's a little bit messy now, so yeah, we're going to have to drag those out. But it's like this one, for example, could be on the bottom like that. This one's on the top, that one's on the bottom. There's nothing wrong with that. That's fine, as long as, you know, once again, like grouping, sometimes you're just physically constrained by the components in there. You can move them around and do that sort of stuff, but you know, 6 of one, half dozen of the other, as long as you're consistent. And just a couple of consistency, tidy up issues here. I wouldn't have those lines there. I'd bring them all down there like that. I know they're different colors. I know the junctions, some junction, like they shouldn't be there, but this is the problems with like tidy up schematics like this. Unfortunately, it's not great. It doesn't look like what I'd normally do, but hopefully you're getting the idea. Now, I'd actually place a port here, because this is like essentially this whole, like, this is like the input block. Okay, so when you're doing blocks like this, generally you wouldn't use a net. It makes no electrical difference. It makes no schematic difference. So you could just have the net there, which is just fine going off, just like you know, just like we had the you know, the nets over here and stuff like that. That's fine, but because they're all within the one block. But when you've got like signals going out of blocks, I generally like prefer to use like a port. It just sort of signifies that it's sort of exiting a block. Once again, electrically, there's no difference whatsoever. Schematic, use a net if you want. I'd just use a port, but doesn't matter. We'll just stick with the net. Once again, I've just put some more label in there. There's different sections, input termination, AC coupling, and this is, I think it's like some sort of input, just selectable input filter in here. I'm not sure of the exact function. On this input filter, for example, like you might put in, like you might have a much more detailed block, and you might actually put in the formula to calculate, or at least tell you what the different you know, frequency components of the filter are, for example. You know, that's just a nice touch on a schematic, so that, okay, it's an input filter, right? So you go from actually, you go from not having that at all, and people have to, guess, oh yeah, it looks like, oh yeah, there's a resistor and a capacitor there, another resistor and capacitor here, this one's got two, they're obviously different values, it's doing, it's doing some filtering, so then the label actually gives you another level of description again, and then if you go in more detailed in there, it can actually give you, this one's designed for, 20 meg bandwidth limit, for example, and it'd tell you that. And then you could often put that right next to which side of the switch it's on as well. So you could physically, make this note smaller and like put it, okay, on this side of the switch, say it might be 20 meg bandwidth limit or whatever, the other one is full bandwidth. Something like that. Adding nice descriptive stuff to your schematics like this is a real big thing. And I did this extensively in my my micro supply power supply project, the schematic for that. I might have to link that one in, but it's got like extensive notes added to the schematic. And this is where I'm going to completely cheat and just copy this from one channel to the next. So this schematic won't be electrically correct. So yeah, sorry about that, but yeah. Anyway, see how it's taken up more space than before, but at least it has some resemblance of signal flow going from one side to the other like that. And because not only do we have the signal flow within the block flowing from left to right, then of course we need to move that literally onto the left hand side of the schematic so that your input signals are over there. Because as I said right at the start, the first thing I'm looking for when I look at the schematic, I know it's a digital storage scope, so I'm looking, right, where are the B and C inputs? I want to start, follow the money. I want to start right at the input, and I want to follow the signal through, like that. So there you go. There's our input section. And if you wanted to get fancy-pantsy, and then if we wanted to, we could add a nice little block around that, and then just label that like input section. Something like that, or input switching, input amplifiers, or whatever. So it just signifies breaking up the blocks of your circuit. So there you go, that's all of our input circuit all over there with the 4 different channels like that, and the signal flows from left through to right into that block, and then it flows out of that block. And as I said, like you might, if you were doing multi-sheet schematics, that would be on its own sheet, for example, and then you'd have ports going out to the next page. But we're just going to keep this to a single page schematic. All right, so we've tidied up the front end. Brilliant. Ugh, this down here, this is ugly. Like, as I said, like this should be a proper op amp to show what's going on here. I definitely wouldn't have chosen the physical pin chip layout here. And then this, the only way we know what on earth this is by its name here, gain switch 2A. So obviously we've got switchable gain AB here. It looks like it's just an analog switch. Actually, yes, a 741G, but I don't know that offhand. But it's looks like an analog switch, but oh, it's just, look at how they've created this schematic symbol. This pin's going off like this, it's going off like this. There's no consistency. Look at the, in your schematic symbols, look at the thick line around here and the thin line around this one. Keep all your schematic symbols consistent, please. And once again, we've got some redundant nets in this part of the section here that's supposed to highlight where else it goes in the circuit. It goes absolutely nowhere. And once again, you might put nets that net names that don't go anywhere if they contain a useful descriptor, for example. In this case, it does. Once again, I've rotated all of these things. I've greatly tidied up this because it just looked like shocking. I've even tidied some of that one up, right? It looked really bad. So if you wanted to keep those net names, that's fine and dandy. By all means, do that. Stretch it out like that. You have to fix this one up here and then put your net names in there. No wuckers, look at that. Then just once again, line them up properly. Snap grid's not working properly here. Ordinarily you'd have a nice snap grid. There you go. And that looks actually quite reasonable. And I've taken out the line that actually goes through the chip here. So you can tell okay, this is the output of the op amp, so it doesn't flow. This is where the op amp schematic symbol would have actually been nicer than just the physical layout of the chip here. Okay, but you can see that the output of, so it's actually the signal's flowing back this way, which is not really, you know, it's not terrific. So it's flowing through this analog switch here. It's flowing through either of these gain resistors here with just some compensation capacitance either side, and then it's coming back to the negative pin. So that's like the feedback on your traditional op amp circuit. So yeah, that's not the best. And then, like, where's our input signal? Here it is in A-1, which, well, it should be coming from somewhere. I think it should be coming from our, yeah, in B-. Okay, so it should be coming from our thing up here. I just haven't got my net names properly. So it comes from here over to here. That's no good. We need to physically move it. Okay, so we want our gain stage to be right next to, right, so we've got our input circuit, then the signal flows, remember, from left to right into our gain stage. So now I've got to move our gain stage up here. I'm going to keep this max chip, but hang on, we need to bugger this off. Oh, so let's drag this one. It's horrid. It's horrid. Oh, the humanity. The humanity. But anyway, let's keep it consistent because we want to follow 4 gain stages like this. So we want them to be nicely in line and flow from, once again, left to right. So we pretty much have to redraw this abomination. But we're going to stick with the one chip between the 2 channels, because even though that's the worst schematic symbol ever for an op amp, it's like, why is it elongated like that? And like, just, let's just not go there. And I just noticed this capacitor is actually upside down. By convention, the flat plate of this capacitor is the positive one, even though this symbol doesn't have that, and it might not be a polarized capacitor. It's just wrong. It's just wrong. Okay, so this isn't ideal, and I don't like it at all, but for the expediency of doing this, I'm just going to leave that chip there. But as you can see, it would have been much nicer to have like an actual op amp symbol there. But anyway, once again, I don't like that at all. But as you can hopefully see, this will at least be consistent when we duplicate this. Once again, I'm for the expediency of this, I think I'll just delete all that. So this won't be electrically good. I've given up trying to make this an electrically good schematic. It's too much work doing this in Out, and it's probably more than enough work doing it in Eagle. But anyway, so but at least it'll visually look good at the end. As you can hopefully see, this is now starting to make some flow sense like this. Input block over here goes into input gain stage, and then that will flow out into our ADC over here. Beauty. And once again, I might add some notes in there. It's not the tidiest, you know, thing. I can space it a bit better. But once again, this is the gain stage. I'm not sure of the exact gain here, whatever it looks like, you know, ×1, ×10, or whatever. I'm not sure, you know, semantics. Doesn't matter. So there we go. We can just add some text. Input stage like that. Gain stage like that. No wuckers. And now we have our ADC. So we need to now tidy that up. And so hopefully you can already see the improvement with our signal flow like this. We're going to flow into our ADCs. And if you remember our original schematic like this, okay, here was our input. It flowed down like this. It somehow went around our op amp like this, and then went back up past the input stage up to the ADC up here, and then somehow into these analog switches over here, and then it goes from the output of this over back right, so it's flowing back left into the FPGA, and it's just nuts. So already you can see that we're going to signal flow through the different stages. That's why an oscilloscope like this is a classic example of multiple signal stage flow like this. It lends itself very well to a schematic, like a nice visual schematic. Actually, what we have to do is actually sneak another stage in here, because this is actually the oversampling stage. Here it is here. So it's actually got to go in here because this is where it routes the signals, either all 4 channels into the ADC or into the, because we've got 2 ADCs, dual channels each. So that either routes all 4 inputs through to all 4 ADCs, or it actually duplicates 2 of the channels down into the other ADC so that you can get twice the sample rate. So really, that block physically, in terms of signal flow, should go in here. Even though it's just these 2 little dinky analog switches here, it needs to go here. It's part of the signal flow. Keep getting left and right on the camera. It's really weird. You've got to think backwards. Now, it's this stage of your schematic that you start deciding, well, I just don't have an infinite amount of room going across the page like this, so we're going to have to wrap it. But there's our 4 stages: input stage, gain stage, oversample selection, and ADC. Then the ADC flows into the FPGA down here, and it looks like most of those pins, D4C and all that there, looks like they're all down the bottom here. So if you still had room to flow it out like this, then you would arrange the pins on your ADC so that the outputs, and you'd arrange the pin out on your ADC here, because you'll notice that the pin out of the ADC is not in physical pin format, so you have the freedom to move those pins anywhere you want. You would group the digital outputs here on the other side of the chip. So when you're creating the schematic component for this MAX 19506 ADC, you'd have the analog inputs on one side and all your other miscellaneous clock and stuff like that. You'd have, this is like arse about. Like, I'm not going to go in there and start modifying components to make this schematic absolutely perfect. Sorry about that. But you would have, you've got analog on one side, analog input, clock inputs. You don't have to separate your analog from your digital side like that. You do it signal flow. So it doesn't matter whether there's analog signals coming in or digital signals coming in, they should be on the left-hand side of your chip. And then your outputs, i.e. your digital outputs like this, should all be, and maybe power, well, you could say power is an input as well. You might put that, it doesn't matter which side you put the power on really, but it might put them on the top and bottom of the chip, for example. That's very common. But once again, don't want to start a flame law, but there are those who never put pins top and bottom of your chips because it just doesn't look right. They like having all pins on one side, including power and ground, or like inputs, and all the outputs on the other side. Whichever way you want to do it, doesn't matter. But this one's side of, they didn't put any thought into this schematic component, and you should put thought in, which is another reason why you shouldn't just use the library component supplied with your schematic package, because I know it's easy, but then it doesn't make for a good looking schematic. It's just hard. Often, you know, it'd just be in like physical pin configuration, and for an ADC, nah. Redraw the schematic symbol so that the signals flow in to out. But I'm not going to bother doing that. But if you could, then you could have all the input signals then just going out the side of this thing and straight into your, and then you'd put your FPGA over here. But we don't have the luxury to do that. We kind of, oh no, we could put the FPGA over here, but I'm already using an A1 schematic sheet. So yeah, it's all a trade-off. You might put it on, you know, as I said, you might have all this on one schematic sheet. This could all be like your input stage and your conversion. You might have that on one sheet, and then you might have your digital processing and power supplies on the other sheet. 2-sheet schematic, that'd be quite reasonable in this particular case, I think. Right, so now I'm going to create a power supply block over here like this. You can put it, you know, anyway, like it doesn't matter. I have power supply block, then I have CPU block, then I'll have an output block like this. So we're getting tidier, and oh, we got an indicator block as well. So we're getting tidier and tidier. Where else have we got some? Is that it for our power supply? I think that might be it. Neat. Where's the input? Where's the power supply connector? Because you want to include the power supply connector. That's on the USB. Where's our USB connector? No. There it is. We want that to be over on the other side too, because, well, so we're going to have to include the power supply and our, it looks like we've got a serial, is that an FTDI thing or something? So we'll whack that over there too. So on our old schematic, look, this was a real mess. Like right in the middle of the schematic is where you don't want to have your 5 volt, your USB and 5 volt power input. So look at, like, it's just, so I've put it over here. Here it is. So your 5 volt input from here goes into your switch. No worries, your switch is on or off. It's not the best switch schematic, as I said, but then it comes in 5 volts, Bob's your uncle. No worries. So, and then we put our ground like that. That's never have anything at 45 or odd degrees like that. Bingo. Okay, we've got our input, and then we can put our data lines going into our chip because we've got to cross them over like that. It's not the best here. Here we go. the alignment's not the best here. Please forgive me. Okay, there we go. That's much better. Now we're talking. But oh, look at this. This is a bit higgledy-piggledy, isn't it? So let's move our capacitor over there. Jeez, what a shocker. Terrible Muriel. Anyway, there you go. There we go. And we've got some pin numbers like on crystals and stuff like that. You don't need your pin numbers on your crystal. Like, that's just like having pin numbers on your capacitor or your resistor. It's just, you know, it's just pointless. And the 3 volt, 3 volt rail like this, that obviously, that's dicking around. So we'd actually duplicate that. You wouldn't run another one over on the other side. Like, you wouldn't run a wire over there. You could, but it's probably just needed to go like that, for example, for the ground. And the ground, oh, it's upside down. So whether or not you'd actually have it going all the way through, some people would prefer that. Others would prefer to snake it up. I'm not that fast. I'll just take it through. But there's a lot of argument to be made that you wouldn't take it all the way through like that. But from a clarity point of view, it really doesn't matter. And then our net labels are all screwed. Great. And there we have it. That is much neater, isn't it? Now, we could, it depends on whether or not you wanted thin, like 5 volts. I wouldn't quibble about that. Like, I would probably just leave that as a square block like that, and then that becomes our input power block, for example. It doesn't matter if you include, like, the serial interface inside an input power block. You can branch that out if you want. Doesn't matter. But there you go. That's more sensibly grouped in our schematic. 5 volt power in, and once again, like, the 5 volts here isn't really obvious, so we'll tidy that up. I would question the use of 3 capacitors here on the input to a voltage regulator. That's just not really needed. So anyway, I'm not going to go into electrical design here, but obviously this is completely arse about. We need to flip like, but yeah, obviously our capacitors need to come down like this. Our ground needs to come around like this. Here we go. Now we're starting to tidy this up and making it look like a much more sensible schematic. As I said, power ports on the top, grounds on the bottom, like that. There we go. That's looking better. Now we're talking. And just a small one here, this LED, for example, you wouldn't, like, have LEDs vertically. There's no reason to not have the LED like that and the resistor like that. That's just like a more industry standard. There we go. That's just a more sensible solution for your LED like that. It just, you know, people expect to see them. Once again, we don't need that visible. That's the component footprint, and we just fix that up like that. And by that's a little bit messy. You'd make it more compact or whatever. But anyway, that's much nicer. And this, you just wouldn't have your line coming down like that. And that for your power stuff, just make them all even. I'm trying to make it even. Once again, it's the grid thing. Okay, you make it even like that, just so it looks nice and tidy. And just one thing, you would never have a 4-way junction like this. I know there's 2 junctions in there. Sorry, this junction. I'm serious. I can't get this importing this Eagle file is just screwed up everything. This schematic is not what it would look like if I just laid it out from scratch. It's just, it's horrid. I hate it. Anyway, you should never do a four-way junction like this. Assume that's a four-way junction with just the one junction in there, because when you print it out, you may lose the junction in there. Like, you know, it comes from the old days when you would print these things out and the resolution wasn't great and you weren't sure if that was just a wire crossing over like that without a junction or whether or not it was a four-way junction. So just as a industry convention, you shouldn't use four-way junctions like that. So you should like stagger them like that. Some people go like when the thing comes down, they go like that. And however you want to do it, you shouldn't do a four-way junction like that. So yeah, just avoid those. Okay, so we separate those, power and USB input. So got our nice looking blocks now. We've got and then we'll probably put the processor one in here, and that makes sense. And then maybe, I'm not sure what's going on here, and maybe some output connectors over on the right hand side over here. Here's one thing you wouldn't do. Look, I didn't even see this tucked away in here. Here's the reset switch. Oh my, like, what? Definitely need to get that switch out of there. That's greatly disturbing. We really, this isn't the best, but there you go. We'll take that in like that. That's our reset switch. Oh, no, then you got your 10K going up there. Look, I'm not going to dick around with that, but obviously you wouldn't do that, right? And once again, we've got our upside down ground symbol. If you're going to do it, at least do it like that, please. And again, like having the designators, if you're going to put them vertically like that, there's the parameter, 10K. See, now you wouldn't mix these up like this. Like it's okay to have it like that, one on one side, one on the other like that, if they're both close together like that. Or, you know, once again, you could flip these around and that's much more readable. And once again, you'd ensure that they're all lined up, but you'd be using a proper snap grid there. There we go. That looks a bit better at least. Once again, all these nets, you would actually rotate them all. I'd actually have these all rotated around like this, but like I'm not going to fuss. I've already mentioned all these details before, so I'm just going to tidy up this bottom bit, and then I'm probably done on the processor block. Like I don't even want to know what went on here. This is just so tidy that up. There's our cap. You probably wouldn't have it coming like across those two. See, now the problem here is that these are all like too close. So I'd say you probably gotta like drag those out like that so that then you can put your designator on one side and your value on the other. The alignment's a bit how you doing, and those junctions shouldn't be there, but you get the idea. Now here's the other thing, is that they've labeled this, like the designator is not R20, R21, etc. They've given it descriptive labels like R offset 1. Now, there's pros and cons to this. The problem is that I can understand why they've done this, is because they want that to be visible on the schematic. That's the resistor for the offset 1, but it's, as you can see, like it's very wordy, very descriptive. That's not what you want for a designator. You want to avoid designators on your PCB that are long. There's a reason why they shorten it to R1, R2, R3. You don't put resistor 1, resistor 2, because it takes up physically more space on your silkscreen layer on your PCB. So yeah, don't do that. If you're going to want a descriptive, if you want like a descriptive label on your silkscreen, add it as a silkscreen, add it at the PCB stage where you've got it, you know, you can associate it with the component. You can have another field of your component that you can enable, because like components often have like all these different parameters down here, and you can turn them on, you can add your own parameters, and you can do, you know, all that sort of jazz, and you can make that visible on the PCB on the silkscreen layer later. So yeah, if you're going to do that, don't do it on the schematic. Just call it R1, R2, blah, 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 etc. Unless you have a very specific reason. There might, I'm not saying there's never a specific reason to do that. So that I2C DAC, I think it is, I wouldn't like give that its own. You could give it its own block and say here, you know, here's your offset voltage generation, because the offset voltage generation feeds into your, the gain stage here. it feeds into your offset pin of your op amp up here. So, you know, if you're really keen as mustard, you could like move this up here like this and then have it as its own separate block and then showing those wires going up the clacker right into the gain stage like that. You know, yeah, why not? Let's do that. So we can call that offset DAC. There it is, and that can have its own little section up there, and then, oh, you could actually, you know, physically nicely line that up there. You know, you can go to town with how these things look, and then if you're really fancy, you could put like an arrow. You could either have the wires going up into the block to visually show that they're going up into there, or you could have like an arrow pointing up that goes, you know, offset DACs signals are going that way right up into the gain stage. It's, you know, it's a visual thing, but just having it separated like that, you know, it's probably good enough. But yeah, it'd be nice to actually run those wires into that offset gain stage. So yeah, it's probably going to be a bit messy if I drop the wires down there like that. So I'll probably leave it as it is, but hopefully you get the idea. Need to clean up these ridiculous capacitors that we had over here. So like I said, you'd find the chips that these things are close to and then go put it CODD blah. Once again, call it like C20. Like, come on. Okay, so I just tidied up that section there, whatever that is. It's some sort of connector. I don't like the wires going through there, but I've already said like enough about all this sort of stuff. So I've almost practically at the end of tidying up this schematic. Glad you hung around. Okay, now we've actually got, these are actually I/O expanders. So I'd probably, what I'd do is actually move those into their own block because the FPGA control can come down, and I'd move those into their own little, you know, I/O expander, because they're their own block. Like I/O expanders are a nice sort of like, you know, separate building block type thing. You can include them in your processor down there, but we'll just separate it because it's nice. There you go. Nice I/O expanders. Beautiful. Like I bought one. I'll probably include that down in the FPGA block down here because, well, I don't know. Whatever. Seems like a good idea. Because we've already got some connectors inside our FPGA control block, I'll just include, like I could, as I said, I could have a separate I/O connector block or a separate I/O connector sheet on your schematic, and once again I could have like a visual I/O thing, but hey, I'll just like include those LEDs down there, no problem. So we've got a couple of daggy capacitors over here, and we'll fix those up. We'll whack those just in there, and Bob's your uncle. And we'd try and fit this onto it, like we're A1 at the moment. I don't think we're going to fit it onto an A2. Look at that. We're going to be short. We're going to be short on the A2, so we're going to have to stick to an A1. So, like, once again, here's where this is getting too big for one sheet. Generally, I wouldn't go over A3, for example. I don't mind doing an A3 schematic. A lot of people will stick to an A4, or, you know, for the Yankee equivalent, bloody fool's cap or whatever, legal or whatever garbage that is. So, yeah, we'll stick to A1. I know it's too big, but anyway, there you go. I think that's pretty groovy. You could argue that the ADC and offset, like the FPGA, you could argue should be in here like this, but then, nothing quite fits. That's our open source hardware logo. Once again, this is quite common on schematics. If you're doing an open source hardware logo, it might include it on your schematic as an actual component, because then the component, you take it from the library, and then you've already got the layout on your PCB, and then it just, when you forward annotate and push over to your PCB, your logo will appear there. You won't have to remember to put the logo over later. So it's a shame that the offset, look, it's almost there in terms of like a square thing. Oh, we almost. Oh, we've come a gutser right at the last minute, have we? Oh, it's terrible, Muriel. Nah, all right, I can tighten this up a bit. I got some wasted space in here. I can push some of these capacitors over. I can push some things over and get around that. I'm going to go to the extra effort. Going to go the whole hog. Well, half hog. There we go, look at that. Just bought ourselves some extra space in there, shuffled the connectors over here, and thing of beauty. It's a joy forever. Look at that. Freed up our space. We can move our entire FPGA block over a little bit. Fantastic. And now we've got room, kinda, sorta, just got room for our ADC offset. Once again, you know, you could visually like muck around with a few of these things. Like I can make those IO expanders vertical, for example. I can put it one under the other. In fact, I might do that. Look at that. There you go. There is our completed schematic. Winner, winner, chicken dinner. So there you have it. I hope you enjoyed that. Thanks for sticking around if you did. I hope you learned something, how to turn this higgledy-piggledy dog's breakfast into this rather, you know, nice-looking modular schematic like this. Once again, this is not the best example. It is not electrically correct, so sorry, I cannot actually re-export this and upload it to the GitHub or whatever. This is just an example, show you how to visually lay out schematics using, you know, industry practice. Once again, from left to right, signal flow, stuff like that, modular things like this. I like putting things in blocks. Once again, I said I'd put like some formula notes. I'd now go through and like add a notes stage where I add, you know, little notes like this, maybe little formulas, little, you know, frequency ranges or whatever for those filters or whatnot. The offset DAC here, I might put a note with like the voltage range of the DACs, for example, and what that, you know, what it corresponds, what full scale of the DAC corresponds to, something like that. You know, and maybe the FPGA control needs some tidy up in terms of the connectors and stuff like that. But hopefully, like, you can see that if you load it, it's not the best schematic. I'm not proud, not particularly proud of the exact job I've done here. It would have been different if I was laying out this from scratch, but it still would have flowed exactly like this. Signals come in on the left, they go through the input stage, gain stage, oversample, ADC. So it's, you know, it's just not as neat and tidy as it would be if I did it from scratch. And as I said, some of those op-amp symbols and stuff like that just aren't good enough. And optimizing the pin configuration, because it's a big decision whether or not to go for that hardware pin configuration that matches your schematic, matches your pins, match the physical chip on the board. It's great for troubleshooting, not so good for understanding how a circuit works, but some chips, like op-amps, lend themselves better to having the actual op-amp symbol, the actual triangle with the positive, inverting, non-inverting inputs and outputs. Because, you know, if you look at this gain stage, you don't know what this Magic Maxim device here, unless you've got industry experience and you go, oh, a gain stage has probably got an op-amp. Oh yeah, that looks, it's a weird symbol for like a weird layout for the chip, but I can see it's got in positive and negative and out. It's obviously a dual, an 8-pin standard pin out, 8-pin dual op-amp, stuff like that. But, you know, and once again, this sort of gain switch here, for example, you would have actually, if you were drawing that symbol, you would have drawn in the actual switch in there. You would have gone to the effort. So rather than just being like a box there, try and often when you're drawing, it only takes you like tens of seconds to add in, when you're drawing a symbol, to add just a little graphical thing of what's happening inside there, you know, stuff like that. So some chips like that, just that analog switch there, lend themselves to some nice little graphics inside there. But it's, you know, to me, an experienced engineer, it's obviously this is like an analog switch, A, B, X on the output, A, B selection here. But for someone who's not that familiar, you know, it'd be nice to actually see the, you know, the switch in there, toggle, something like that. So yeah, this, to get this looking, I would not release this. I'd tidy it up a lot more and, you know, do some other stuff. I've still got an upside ground symbol. All the electrons are going to fall out. Oops, 2 of them. There you go. But anyway, hopefully you learned something of how to lay out schematics like that. And as always, yeah, flame comments down below. There's more than one way to skin a cat on a schematic. There's many different ways, and everyone has their own particular flavor and technique of doing schematics and things like that. But there's some industry conventions like that left-right signal flow and just modular blocking and stuff like that. So anyway, hope you found that useful. Don't know how long this video has been, 45 minutes, an hour. Sorry, it's just how long it takes. Extra waffle. If you liked the video, give it a big thumbs up, and as always, you can discuss down below, EEVblog forum, and there's videos at the end here somewhere. Watch them. Catch you next time.